Alright guys, so we're going to do the notes from Tuesday. So we're going to start with the title, that's Gravity. Our focus for this notes is that gravity is a force that is applied and not something that's just happening. So it has to have interaction with something else. One of our misconceptions, the things that people kind of get confused about, is the difference between weight and mass. And so we're going to look at mass first. And mass is a physical property of matter, or it's like how much stuff is there. The mass of an object doesn't change when gravity changes. So if I weigh cheese, if I weigh cheese, he's 17 pounds on Earth, but his mass is like 23 kilograms. Like that's how much mass he takes up. If I were to weigh him here, he's 17 pounds. If I weigh him on the moon, then he's, I think, like 2 pounds. Like he's really little. Because weight, if you look at the side on the right, weight is the effect of gravity on something's mass. So weight's really like how much is gravity pulling on an object. Your weight changes depending on your altitude even, your gravity's pull, because as you go farther up, there's less pull from the center of the Earth. If you go to different planets where there's different gravitational pulls, so mass doesn't change. It is constant, forever, forever. Weight is fluctuating based on gravity's pull. So the picture here in the screen is talking about how the mass of an elephant, there's more mass of an elephant. So if I pull it, if I'm those 3 kids in the picture and I pull the elephant, no matter how hard I pull, that elephant's like 3-ton mass is no match for my, like we'll say, 200-pound pull that these kids are doing. The mouse, on the other hand, on the top of the picture, has far less mass. So the kids are able to move it a little easier. Weight, remember weight is the pull of gravity on an object. So with the elephant, if I weigh the elephant on the surface of our planet, it's going to weigh like 2 tons. Whereas if I go up to the moon and weigh it, it may only weigh a couple 100 pounds. So let's look at the definition of gravity. The top one is the actual definition, like textbook. Gravity is the tendency of objects with mass to accelerate towards each other. Basically restated, gravity is a trend of objects with mass to move or be pulled towards each other. Gravity is one of the 4 fundamental forces. The ones that we're going to talk about this year, we're going to talk about all of them. First one is gravity. Then there's one called weak force, which is really important when we talk about chemistry. And then there's centrifugal with an F and centripetal with a P. And those have to do with circular motions, and we'll look at those when we do weather. So Mr. Tycho Brahe, if you had Wednesday school, you know all about him because you read all about him. But for your notes, all you need to understand is that Tycho Brahe used gravity to help argue that the motion of our planets are around the sun and not around the Earth. So he argued that because the sun is so much bigger in mass, it would have more gravitational pull, therefore beginning to make our celestial bodies, our planets, our stars, our moons that are around us, move around the sun. Kepler, you don't need. Mr. Isaac Newton, you need to understand he's the first guy to really theorize or write down the law of gravitation. The other big key, see if I get a mouse here, no, is to understand that he worked with math and chemistry predominantly before he found a love in physics. So if you look at the bottom kind of yellow box there, it says that he put physics and math into Kepler's laws. So he took this guy in his work with how things move in our solar system and he applied the math to it so that people could really understand it, and he really helped prove some of their theories. So Newton's laws of motion. If, and I know some of you can, if you could tell me what these 3 laws are without looking at the screen, without looking at a notebook, without looking at the board, then you don't need to rewrite these down. However, if I were to ask you what's the first law and you said, then you need to rewrite it, because just like we talked about with SMART, there's research behind writing things down. So if you haven't written it down properly, then write it down again. Maybe it'll be the time that it sticks. So first law is that a body is going to either remain in motion or still until a force acts upon it. The second law is the amount of force needed to move an object depends on its mass, which is force equals mass times acceleration, that equation at the end. So if I'm like a 5-year-old and I want to push Mr. Schindler down the hall, there's a lot more force needed for that 5-year-old to be able to move Mr. Schindler. Now, if it were reversed and Mr. Schindler is going to push the little 5-year-old, he's got more force in his own body, so he doesn't need to exert or use that much force to move that small massed little body. The third law, and the biggest piece that I need you guys to just drill into your brain, is that forces are always paired. If the first interaction is for it to go left, then the reaction is to go right. If you look at car crashes, if a car is driving straight down the freeway and somebody hits it from behind, the hit from behind is going to cause the motion of the car to keep going forward, or it's going to push it even further forward. Relativity we don't need. Application of second law and Einstein's theory. These two, if you can understand the second law, then you can understand projectile motion, which if you play Angry Birds, that's what second law is. Pendulums, the little Newton's cradles on my desk, those are affected by Newton's second law and Einstein's theory of relativity. And then the last one is black holes. We are going to look really heavily and try to understand what black holes are when we do space, but for our purposes in this unit, we're looking at the top 2, projectile motions and pendulums. So one of the words that I need you to kind of put in your brain, it's on the board now, is trajectory. And that is the pathway that an object follows from like being launched. If you play Angry Birds, this is trajectory. When you pull the little bird back, you watch the little dotted arrow line show up. If you play like Call of Duty and you have to launch rockets, you have to understand where that rocket's going to go to so that you shoot it properly. If you are playing the soccer games on the iPad, you have to understand that kind of arc that some of the soccer balls are going to take. So you have to kind of, mentally follow that path. If you play football and you're throwing a football, you need to understand the trajectory of your football so that you throw it with enough arc so that it goes to the people who are trying to catch it. Universal law of gravitation, the biggest piece you need, because we talked about this in class, this is like a distractor slide. The only part you need to know is that that little bottom part in kind of the maroon colors, and that's that gravity is greater when mass is larger. That's really all you need. So if you know the saying, the bigger they are, the harder they fall, that's really what this is saying. Don't need it. Don't need it. Force meters and spring scales. We measure newtons in spring scales. So if you don't know that, you probably need to write it down. The gravity down under and how people don't fall off our planet. We were doing a customized activity with this slide, but realistically what we summarized and surmised with everybody was that gravity is constant, and no matter where you are on our planet, like if you're in the south of Africa, you're in the north of Spain, you're in India, the amount of gravity applied to you is the same because our planet's gravity is constant. There's a video called The Hammer and the Feather. It's in the links of the description, and it goes with this slide. So the question is, if the astronaut were to drop those 2 objects, what is going to happen to the hammer and the feather? So that's one of those questions. And then microgravity, we don't really talk about it much, but this is why on the surface of the moon, and even in like when they do spacewalks, there's still a little bit of gravity applied because our planet's gravity reaches out past our atmosphere. But there's a question that's not in the slide, and it's about the Futurama clip. And you need to put your answer of what is he trying to lose. So what is Bender trying to lose? And then the second question is, how does he slow down? And that's it. And those two links will be in the descriptions. And I hope that's all. And yeah. So I'll see you guys around school. Okay, bye.